To find the initial rate of change in the population, all we have to do is initial rate means at time 0. So if we want to know the rate of change at time 0, all we need to do is plug in 0 for t. Since it's not like f of x, I can't be like f of 0. So I'm just going to go ahead and say initial means time equals 0. And since we're asking for the rate of change and we know what the time is, we can just go ahead and replace that, use our rate of change formula, our derivative. So that's 4 over 0 plus 1, which just equals 4. So if we want to talk about this in the context of the situation, remember that it's y over x, change in y over change in x, so it'd be like p over t. So what that means is 4, and then p is the population in thousands. So 4,000 people per 1 t, and t is time in years, per 1 year. So initially, at the beginning of whatever model was our original model, p of t, at the very, very beginning, it says, hey, we started out at a rate of change of 4,000 people per year. And then I'm assuming that that rate of change changes as we move on towards whatever is affecting this situation, which we don't know. It says describe how the population changes over time. And so now we need to use our derivative function and look at that derivative function and figure out what is that telling us about the population, the original function. So just kind of like before, we were like, hey, here's our derivative function. What could it tell us about our original function? We're going to look at our derivative function and say the exact same thing. What's going on with our original function? So we do 4 divided by x plus 1. And it looks something like this. Now it does say that x is greater than or equal to 0. So while it is a rational function that does this like crazy, weird, like opposite direction boomerang situation, I'm only going to sketch this graph from 0 on, a little bit before. But really, this is the only part of the graph that we care about, okay? So you can see here this initial rate of 4. This was your original rate of change, was 4,000 people per 1 year. And now we need to talk about a few things. One of the things is that the derivative dp over dt is always positive, right? It's always above the x-axis. And if it's always above the x-axis, then that means with the original function is always increasing. So that's one thing that this derivative function can tell you, is that since it's always positive, we can see that there's got this like asymptote here, which means that your rate of change is probably never going to be 0 when we're talking about a population. So since it's always positive, that means that our slope for this function which describes the population over time, is always going up. Now it gets less and less and less up, right? Like maybe at the beginning it was like really big, and then it starts to taper off of like, hey, we're not growing as much as we were before, some sort of natural forces that are influencing whether or not this population can grow. As it gets closer and closer to 0, it's still growing, but it's not growing as much. So it means that the population is always growing. So that's one thing we can take away from this. And then let's talk about the fact that it's dp over dt, the derivative, is more positive at the beginning and gets less positive. The reason why, or not the reason, but what it means when it's getting less positive is that your rate of change was the largest at the beginning. So maybe your original function looked like this at the beginning, like it was the largest jump at the beginning. And then it's still positive, so it's still growing, but eventually it starts to taper off. So this could be p of t as opposed to dp dt. So that's kind of the idea of what's going on here. And so when it says it's more positive at the beginning and it gets less positive as time goes on, that means that the population grew the most at the beginning and then tapered off. Okay, so again, using our derivative function and understanding what is our derivative and what can I tell us about the original. And that connection is really hard to make, and I'm just somebody who's done this often, and so I can make that connection. But knowing how to take your derivative and turn it into an option for the original takes time and understanding and deep, deep understanding of what this derivative function is telling us, which is why we took so long at the beginning to just be like, what do we mean by the slope here versus the slope there, and how do we get there? Okay, last problem. Given the graph of dy dx shown, write down the intervals where y is increasing and the intervals where y is decreasing. So we have to talk about the fact, again, that this, with the derivative function, right, this is dy dx. This is your derivative function. So we're not looking at where is it increasing on the derivative function. With the derivative function, it's increasing. The original function is increasing when we're above the x-axis. This means that the function is increasing there, the original. This means that the function is increasing on the original. This means that the function is increasing on the original. We know that it's decreasing, the original function is decreasing when our derivative is below 0. Okay, so I want you to go ahead and take your best guess, just using the variables of where is it increasing and where is it decreasing. So fill in the blanks as you see them. So it's increasing. Our original function is increasing when the derivative is above the x-axis. So it's above the x-axis between a and b. So a is less than x, which is less than b. It's also above the x-axis between c and d. So c is less than x, which is less than d. And then it's increasing again here, and we don't know what's going to happen, right? Like that could go like this for forever, or maybe it comes down and then starts to taper off and never goes back below. So we don't know what's happening here. So we're going to say from e is less than x, which is less than infinity. And that's where it's increasing. Go ahead and try again now with your decreasing. So your function is decreasing when the derivative is below the x-axis, So it's below the x-axis from negative infinity, right, all the way down here to a. And then it's below the x-axis between b and c. And then it's below the x-axis between d and e. And those are your three intervals where it's decreasing on the original function. So hopefully we feel a little bit better today about like when is it increasing, when is it decreasing, how do we use the derivative function to know more about our original function when we don't even have the original function. That's it. Good job today.